Let's suppose that we have a function with two independent variables, z equals f of x, y, and we want to identify where maxes and mins occur. Now, we've already in the past studied how to determine how to find the critical points. Well, what we found was we said, well, the partial with respect to x has to be equal to 0, and the partial with respect to y has to be simultaneously equal to 0. So we would find the partial with respect to x, set it equal to 0, partial with respect to y, set that equal to 0, and that's how we would get our critical points. Now, what we want to do is we want to figure out a way that we can identify if those critical points are maxes or are they mins. Okay? So we don't want to just know where the possible high points and low points occur. We want to have a test where we can identify, this critical point yields a maximum, this critical point yields a minimum. So now to do that, let's harken back to how we did something similar in Calculus 1. In Calculus 1, we would have a graph, remember, and what we would do, let's say a graph like this, and this is a function of a single variable, one independent variable. And what we would do is we would find the critical number. We would set the derivative equal to 0, f prime of x equals 0, and we would solve that and get this c1, for example, where, f prime of c1 is equal to 0. And we would say, okay, also f prime of c2 is equal to 0 as well. In other words, we would identify the values that will give us a derivative of 0. And the idea is that that's where the slope of the tangent is 0. So f prime of c1, the derivative is 0 there. In other words, the slope of the tangent is 0. That means you have a max or a min. Okay, so now also, we also took note of this. Notice where you have a max, that corresponds to concave down. So look at that concave down. So in other words, the second derivative at this point is less than 0. And the second derivative at this point, c2, is greater than 0. Now notice this corresponds to a max. This corresponds to a min. Now this is a little bit counterintuitive because you might think, well, I think of something bigger than 0, that's going to be the max. Something less than 0 is the min. But no, you got to think it through, and then it makes sense. Now, okay, we want something similar to that for multivariable, for a function with two independent variables. So let's see if we can figure something out. Now, to do this, let's just think about a quadratic function here, a quadratic function, let's say. Okay, there's a quadratic function. And let's suppose we want to find the zeros of this function. So in other words, I'm going to say, okay, x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So that's how we would find the zeros of that function. Now, we're not going to concern ourselves here with finding the actual zeros. We just want to look at this part that's under the radical, b squared minus 4ac. Because this part here is going to give us a lot of information about what the graph looks like. For example, let's suppose that this b squared minus 4ac is less than 0. That means that you're going to be trying to take the square root of a negative number. That means you're going to get two non-real solutions. That means the graph is not going to cross the x-axis. So what you're going to have is a couple of possibilities. Okay, so maybe you'll have something that looks like this. Now, this means that the a part is greater than 0. In other words, this parabola is opening up, and it's not crossing the axis. Now, you could have something like this if a is less than 0. In other words, if you had like negative x squared, it would be upside down. But it would be one of these two things if b squared minus 4ac is less than 0. Yeah. Now, let's suppose that b squared minus 4ac is greater than 0. Well, then you have two real solutions. And with these two real solutions, you're going to have a couple of possibilities here. You're going to have something that looks like this or something that looks like this. Now notice, let's compare these two. In this situation over here, notice that the function is either always positive or always negative. Now, so keep that in mind. Now, on this one over here, the function is sometimes positive, sometimes negative. See? Sometimes negative, sometimes positive. That's when the b squared minus 4ac is greater than 0. Now, think in terms of the second derivative. That's where we're going with this. So we're looking for something that will tell us, the second derivative is always positive or always negative, or sometimes it's positive, sometimes it's negative. Okay, anyway, okay, let's move along. Now, let's suppose that b squared minus 4ac is equal to 0. What does that mean? Well, then, in that case, you have a bounce. Something like that, or something like that. You have a little bounce going on there. Okay, so let's keep this stuff in mind. Let's keep this in mind. Now, what I want to do is develop a technique for finding out where this thing has maxes and mins. In other words, a function like this. But first of all, let's do the generic. So let's just start off with the generic function. Here I've got z equals f of xy. Now, I want to find where a max occurs, where a min occurs for this surface, no matter which direction, no matter which derivative we're taking, whether or not it's along the x-axis, along the y-axis, in the direction of the x, in the direction of the y, or whatever direction. In other words, I want to look at the directional derivative. And I want to find, I want to be able to say, this critical number gives me a maximum no matter which direction you approach from. Likewise, this critical number gives me a minimum no matter which direction. So what I'm going to do is I'm going to have just a general direction here of u1, u2. So this right here, this is a unit vector. Now, let's find the directional derivative. Here we go. So the directional derivative of this thing is going to equal, here it goes, fx u1 plus fy u2. Yeah, there it is. That's the directional derivative. Nothing more to it than that. But now we want to find the second derivative. So I want to find the derivative of this. So here I go. I'm going to take the derivative, the directional derivative of this thing that we just took the derivative of, which is, I want to take the directional derivative of the directional derivative. Okay, so here we go. Now you have to really be careful here because we're not accustomed to this. I want to take the partial with respect to x times u1. So here it goes. It goes fx, partial with respect to x. Here we go. I take the partial with respect to x times u1. So dig what I've done there. I've just taken the derivative with respect to x, just like usual. So in the case of f partial x here, I just put another x there. In the case of x f partial y, put an x with it. Okay, now plus, now we take the derivative with respect to y. So we have fxy u1 plus fyy u2 u2. Yeah, that's it. That's it. Now let's clear parentheses here and see what we've got. This is the second derivative. We've got fxx u1 squared. Yeah, u1 squared. Plus fyx u1 u2. Plus, now we're over to this one, fxy u1 u2. See, I'm just clearing the parentheses. Plus fyy u2 squared. There we go. Got rid of all those parentheses. Now, dig, if you will, that this and this are the same. fyx and fxy are the same. So let's see if we can write this a little bit different. fxx u1 squared plus 2 fxy u1 u2 plus fyy u2 squared. There. Yeah, that's it. That's the ticket. Now, I know where I'm going with this, so I'm going to do a little something here that you might not, it may not be obvious, but it's just a little trick that's going to get me to where I want to go. I'm going to factor out a u2 squared. So u2 squared. There I go. I factored it out. Now, what do I have left? I have fxx, and here I'm going to have u1 over u2 squared. Now, you can think about that a minute. Just think, if I were to distribute the u2 squared back through, I would get exactly, what I had here. Okay. Now I'm going to say plus 2 fxy u1 over u2. Okay. Now think about that. Just make sure it's clear in your mind. If I distribute this u2 squared, I get this back. And then, of course, this here is fyy. Okay, now I want to do another thing here just to emphasize what's happening. Let's let t equal u1 over u2. Let's just do that, and let's see what we've got. We've got u2 squared. I'm just going to leave that alone. And then I've got this. I've got fxx t squared plus 2 fxy t plus fyy. Look at that. There's what I've got. Now, let's suppose that, let's remember this is the second derivative. And what we're concerned about is, when is this thing positive? When is it negative? Now, this right here, this part is always positive because it's u2 squared. That's always positive. So I'm not going to concern myself with that one. I'm going to concern myself with this part over here, this part right here. I want to know, when is that positive and when is it negative. Now, dig this. Look at this. fxx, let me call that a. Okay, so I've got at squared. Now let me call this part right here b. And let me call this part on the end, I'll call that c. Now, I want to know, so look at this. This is something we've seen before. Look at this up here. We had this, and we studied the b squared minus 4ac to determine when this thing is positive, when it's negative, and so forth. So let's do that. Let's do that here. So here's what I've got. I've got b squared minus 4ac. Well, let's see what that looks like. Well, the b is 2fxy. 2fxy squared, that's b squared, minus 4 times a, c. So here's what we've got now. We've got 4x fxy squared. Okay. Minus 4fxx fyy. And let's just set that equal to 0. Or actually, we don't need to set it equal to 0. Let's just think about what would happen if this is less than 0. Let's just do that. And let me do this. Let me divide out the 4. And I'm just going to divide out the 4 for all the further discussions. See? So here's what we've got. We've got fxy squared minus 4fxx fyy. Actually, look at me putting that 4 in there. I meant to take that 4 out. Forgive me. Okay, fx, x, f, x, y. Yeah. So, let's see what happens. Okay? So in this situation, just like the discussion earlier, look at this discussion we had earlier. This one right here. Remember what we're saying is the second derivative is either always like this or always like this. Either always positive or always negative. Now, what does it depend upon? Well, it depends on A. So, this is fxx is greater than 0. This is fxx less than 0. So this means concave up. This means concave down. So this indicates a minimum. This indicates a maximum. See? In other words, we're saying, hey, the second derivative, if this situation exists and fxx is greater than 0, that indicates that second derivative is positive, which indicates you've got yourself a minimum. Likewise, if fxx is less than 0 and this situation exists, you've got yourself a maximum. Now let's go the other way. Let's look at this. Let's suppose that we have fxy squared minus fxx fxy, and let's suppose that's greater than 0. Okay, let's see what that means. Well, that means you've got something like this or something like this. Well, that means, it could be positive or it could be negative, depending on, it's not a clear-cut case like this first one. In other words, it looks like it depends on the path you take. Okay? So you've got this surface and you've got this critical number. You found a critical number and you're trying to determine, is this going to give me a max or a min? So you're wanting to know about the concavity. Well, this test tells you that it could be positive or negative. You could have concave up or concave down. And what it depends upon is the path you take. In other words, it depends on this thing. Whoops. This thing right. My pen stopped working. It depends on this. It depends on the path you take. Okay? Now, so when that happens, we say we have a saddle point. A saddle point. Okay? Now, if you go if you go the last step, b squared minus 4ac. So let's look at this. We've got fxy squared minus fxx fxy equals 0. If you have that situation, we say this test, the second derivative, the second partial test is inconclusive. It's indeterminate. We don't know. Okay. So if we have this situation, we don't know. So we're looking for where it's less than 0 or where it's greater than 0. Now remember when we did the second derivative test, when we plugged in the critical number in Cal 1 and we got the second derivative 0, the test was inconclusive. Same situation here. Now, what I want to do is I want to look at this function here. So let me see if I can move it down here a bit. Whoops. Hang on. Oh, there it goes. Copy. I was trying to copy it. There, copied it. Okay, now let me see if I can paste it. Paste. Ooh, hot dog. Got it. Okay. Now, let's suppose I want to go through the whole process of determining where the maxes and mins are on this thing. So here I go. I'm going to take the first derivative, okay, with respect to x. Now, if I take the first derivative, the first partial with respect to x, I'm going to get negative 3x squared plus 4y, and that's it. I'm going to get that. Now let me take the fxx. Well, that's just going to be negative 6x. Okay. Now let me take fxy. Okay. Well, that's just going to be 4. Right? Okay, now let's do the partial with respect to y. Partial with respect to y is going to be 4x minus 4y. And then, yeah, I think that's all we're going to need to do. Oh, fyy. Almost forgot. Fyy, so that's just going to be negative 4. Now remember, I just need all these parts. Okay. And actually, I messed up here. This is yy. Sorry about that. This is yy. Man, I did it on both of those. Yeah. Okay. Man. Okay. Here we go. Sorry about that. Man, you got to keep your head on a swivel here. You can mess up so easily. Let that be a lesson to you. Okay. Yeah, I did that on purpose. No. Okay. Okay. Now I got it. Okay. So I believe we've got it now. So now let's. So be sure. By the way, just be sure you understand what I did wrong here. This has got to be fyy, 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 and I just messed up there. Okay. So I made a mistake. It's fixed. Now we go on. Okay. Just be sure you catch that mistake in your notes. Now, remember, to find the critical numbers, we need to take the partial with respect to x, set that equal to 0, and the partial with respect to y, set that equal to 0. Okay, 4x minus 4y. And we solve these simultaneously. Now, for this one here, we get x equals y, for the second one. And then let's see what we've got here. We've got then negative 3x squared plus 4x equals 0 because x and y are equal. Now, if I do that, let's see what I've got. Now, I want to factor out an x. And I've got negative 3x plus 4 equals 0. That means that x equals 0 or x equals 4/3. Okay? Okay, so we've got, and since y and x are equal to, we've got, since x is equal to y, we've got these two critical points, 0, 0, and we've also got 4/3, 4/3. Yeah, like that. Now, it's time. So we're thinking, okay, these are candidates for maxes and mins. Now let's use 0, 0 first of all. Now remember, what we're going to do is we're going to take the fxy minus fxx. See? fyy. Okay, now let me plug in. So fxy squared, so let's see here. fxy is 4. So this is going to be 16. See, fxy is 4 minus fxx. Well, negative 6 times 0 times fyy times negative 4. Well, that is just 16, which is greater than 0. Okay, so we've got a situation here where it's greater than 0. So what did that give us? Whenever it's greater than 0, we've got ourselves a saddle. Okay, so a saddle point at 0, 0, f of 0, 0. Okay, so just plugging in to get the triple. Yeah. And I guess it'd be easy to compute this. This is going to be 0, 0, 1, because f of 0 is 1. F of 0, 0 is 1. Okay, so we got a saddle there. Now let's try this other one. Same thing. So I've got 16 minus, okay, let's see here, 16 minus fxx. Okay, fxx, that's negative 6 times 4/3. Okay, times fyy, well, times negative 4. Okay, so let's see what this gives us. This gives us 16, and let's compute this, plus 6 times 4/3 times negative 4. I'm just going a step at a time here. So this gives us 16, okay, plus 8 times negative 4, which gives us 16 minus 32, which gives us negative 16. Now that's less than 0. Okay. Now if it's less than 0, then so we've got a situation like this up here. Less than 0. That tells us we either have a max or a min. So it's all dependent upon fxx at 4/3. That's what it's dependent upon. Now, so let's see what this is. fxx is negative 6 times 4/3. Well, that's going to be less than 0. So let's see what that gives us. If this is less than 0, then it looks like we have a max. Okay, so dig what happened. This right here, this is less than 0. Okay, negative 16, and fxx is also less than 0. So that tells us that we have a max at this point. 4/3, f of 4/3. In other words, when we plug that in. And that is the second partials test.